Piping vibration, surge and momentum changes due to valve operation, mechanical effects in piping systems from valve actions. Significance of surge in piping systems, introduction to surge and momentum changes. Surge, commonly referred to as water hammer, is a critical phenomenon in piping systems that occurs when fluid momentum changes abruptly due to rapid valve operations or pump transitions. This sudden change generates high-pressure waves that propagate through the system at sonic speed, creating transient forces that can exceed design limits. Surge events are particularly hazardous because they can lead to severe mechanical stress, fatigue failures, and even catastrophic ruptures in pipelines. The significance of surge lies in its ability to compromise system integrity within seconds, posing safety risks, operational downtime, and costly repairs. Understanding surge mechanisms is essential for engineers to design robust systems that can withstand transient conditions and prevent failures. Surge is not limited to liquid systems. Multiphase and even gas systems can experience momentum-induced forces during rapid operational changes. The phenomenon is influenced by factors such as fluid density, velocity, pipe length, and valve actuation speed. Inadequate consideration of surge during design can result in overstressed components, damaged supports, and compromised safety valves. Therefore, proactive surge analysis and mitigation strategies are integral to piping design and maintenance programs. How surge occurs and propagates, mechanism of surge and transient pressure waves. Surge occurs when a moving fluid is forced to stop or change direction suddenly, typically due to rapid valve closure or opening. When a valve closes quickly, the kinetic energy of the fluid converts into a pressure wave that travels upstream at the speed of sound in the fluid. This pressure wave reflects at boundaries such as closed ends or vessels, creating oscillations that can persist until dissipated by friction or damping mechanisms. The magnitude of the surge pressure is proportional to the fluid velocity and density, and inversely related to the valve closing time. For example, in liquid systems, the Joukowsky equation estimates surge pressure as delta P equals ρ times A times delta V. Where ρ is fluid density, A is acoustic velocity, and delta V is the change in fluid velocity. These transient waves impose dynamic loads on pipe walls, supports, and connected equipment, often exceeding static design pressures. In multiphase systems, surge effects are more complex due to compressibility and phase interactions. The rapid propagation of pressure waves can cause severe vibration, fatigue, and overstress failures if not properly controlled. Understanding this mechanism is crucial for implementing preventive measures such as controlled valve actuation and surge suppression devices. Operational triggers and surge behavior, causes and characteristics of surge. The primary causes of surge in piping systems include rapid valve closure or opening, emergency shutdowns, blowdown operations, and pump startup or shutdown. Fast-acting valves such as emergency shutdown valves, ESD, blowdown valves, BDV, and relief valves are common culprits because they alter fluid momentum almost instantaneously. Surge characteristics involve high-pressure spikes that propagate at sonic speed, creating transient forces that can damage pipe supports, anchors, and connected equipment. These forces are not localized, they travel throughout the system, affecting multiple components simultaneously. The severity of surge depends on fluid properties, pipeline length, and valve actuation speed. Longer pipelines and higher fluid velocities amplify surge pressures, while shorter valve closing times exacerbate the problem. In extreme cases, surge can exceed the pressure rating of flanges and joints, leading to leaks or ruptures. Surge events are often accompanied by audible noise and vibration, which serve as indicators of transient stress. Engineers must consider these characteristics during design and operation to prevent failures and ensure system reliability. Consequences of surge-induced forces, impact on piping integrity and safety. Surge-induced forces can have devastating effects on piping systems. The sudden pressure spikes and dynamic loads can cause overstress in pipe walls, leading to fatigue cracks and eventual rupture. Supports and anchors may fail under the excessive loads, resulting in misalignment and further mechanical damage. Small bore connections and welded joints are particularly vulnerable due to their lower fatigue resistance. In addition to structural damage, surge can compromise safety systems by overstressing relief valves and blowdown lines. The short time to failure during severe surge events means that catastrophic accidents can occur without warning, posing significant risks to personnel and equipment. Environmental hazards such as fluid leaks and explosions are also possible outcomes. Therefore, surge management is not only a design consideration but a critical safety requirement. Implementing preventive measures and monitoring systems can mitigate these risks and ensure compliance with industry safety standards. Design and operational strategies, preventive measures and best practices. Preventing surge requires a combination of design modifications and operational controls. Key strategies include slowing down valve actuation to allow gradual changes in fluid momentum, thereby reducing pressure spikes. Surge tanks or accumulators can be installed to absorb excess energy and dampen pressure waves. Pressure relief systems, such as fast-acting relief valves or bursting discs, provide additional protection by diverting excess pressure away from critical components. For pump systems, implementing soft start and controlled shutdown procedures minimizes sudden changes in flow velocity. Pipe routing should avoid long unsupported spans and incorporate adequate guides and anchors to withstand transient forces. Computational surge analysis during design helps predict potential surge scenarios and optimize mitigation measures. Industry standards such as API guidelines recommend specific practices for surge control, including valve sizing and actuation timing. Regular maintenance and inspection of surge control devices ensure continued effectiveness. By integrating these preventive measures, engineers can significantly reduce the risk of surge-induced failures and enhance system reliability.